Good morning. Day 6 today. We're going to look at nuclear fusion and nuclear fission and chain reactions, and also finding the energy that could be released in a nuclear fusion or fission reaction. Okay, and what the difference between the two are and that kind of stuff. So we're waiting for our board to open here. And then we'll get started on those topics that we're going to look at. Okay. In this last unit, remember the last unit will have a hand in, but no quiz to it. We'll just have that put on the final exam, I think, as we're getting into June here. And I want to have a buffer zone of a week or so, at least, so that people can catch up if they're not in the same place as everyone else. Okay, so let's get this set up here first. Okay, so this is day 6, unit 4, and we're going to be looking at what is a chain reaction, we're going to be looking at what is nuclear fusion, what is nuclear fission. Okay, and then we're going to be looking at an example energy calculation. With either or fission or fusion. Okay, so let's start off with basically a chain reaction. Where are we here? There it is. Okay, so when we talk about, well, actually, maybe we should start with fusion. I think there's only one S there. Sorry. Oh, actually, no, we'll start off with a chain reaction. Okay, so if we get a chain reaction. Okay, so when nuclear fission occurs, one neutron can start a chain reaction, okay? Controlled chain reaction is usually what happens in a nuclear power plant, whereas an uncontrolled chain reaction occurs in the bombs, right? Nuclear atomic bombs. And what happens basically is you're splitting nucleus, okay? So chain reaction, this can occur when a neutron splits a nucleus which releases more neutrons to continue the process. Okay, and it looks something like this. So if we have a neutron, let's draw it out here. If we have a neutron, which is just a nuclear particle, right? And it's a slow-moving neutron. And if it's coming along and it splits a nucleus, a radioactive nucleus. So let's make a nucleus here. Put some protons, which we'll do in blue here. Some neutrons in there as well. which we'll do in black. Okay, it strikes that. Okay, and it splits this. Okay, it splits the nucleus. So what we have, depending on, with uranium-235, it splits into 3 actually, but it could be just 2. Okay, let's just do 2 so that it's not so bad. Okay, and it releases so we have 2 daughter nuclei. So these are smaller. Okay. Okay, we got some daughter nuclei, and then also, I should do it in black here. It's also releasing some free neutrons. So let's do 3 here. I should have put this near the middle of the page here. Okay, I got 1 there, 1 there. Let's do a 3rd one here. Okay, it releases. I would like to do it up there, but I should have put that down a little further. Okay, and then these neutrons go and they strike large nuclei again. That one's going for that one, that one's going for that one. Okay, so this is going to split. Okay, so off of this one, we're going to have another split. Okay, so this one's going to release 3 more neutrons. This one's going to release 3 more neutrons, as well as the daughter nuclei, but we're not going to draw those again. And this one's going to release 3 neutrons. So you can see that it's going to grow into an exponential equation. It's going to be 1, 3, 9, 27. Okay, and it's going to, okay, it has exponential growth of this chain reaction. So this is a chain reaction picture, splitting from 1 to 3, well, 2 in this case, or whatever, 3 released neutrons. And then we have 9 and so forth. So we can see that the chain reaction, let's type it out here, make it neater. Okay. Basically, if we have a chain reaction, okay, this is grows exponentially. And releases energy as it goes. You know, what happens in a nuclear reactor is they have control rods in there to absorb fast-moving neutrons so that we don't have a meltdown. and they can control the rate of the reaction by absorbing these neutrons that are released in the reaction. Then they control the speed, they keep the speed down, and they produce this energy that then is used to drive turbines or whatever. Okay, it's exponential growth, release energy as it goes. In a reaction, in a controlled nuclear reaction, energy is produced and the speed of the neutrons are, are controlled in a reactor core by absorbing many of the neutrons. Okay. In an explosion, critical mass is needed, enough of the nuclear material to explode. And the reaction proceeds so fast that an explosion of energy is released. Okay, and critical mass means is enough radioactive material to produce an explosion. Okay, so how they did it in the old days with the atomic bombs that they dropped in World War II and stuff like that is they basically had this nuclear material in the fins of the bomb, actually, or in the container of the bomb, the beryllium sphere. What they did was they could detonate this bomb, so they would drop it, and they found that if they detonated it over the ground, there's more damage. And then with these, it's kind of like this. I'll draw it for you. I'm not going to ask this, but in case you're interested. The old bombs that went over Japan, they kind of had a reaction core like this, and then they had these 4 fins with nuclear material in them, like this. Okay, and then this would give them access to the nuclear core. So they had radioactive material here, 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 and here. Okay. Which was enough for critical mass. And then on the outside of it, they just had tiny charges. And what they did was they blew this, and it would force the nuclear material into the chamber, creating a chain reaction with critical mass, and boom, explosion occurs. Okay, and that's kind of what they did in the historical atomic bombs. Nowadays, they have more sophisticated uh, technology that they use. Okay, so the next thing I wanted to look at was fission and fusion. Okay, let me just get my preview up here so that I can see how we're doing in terms of time. Come on. It's not letting me do it here. Let's go to the next page and I'll set that up and then I'll look for it. Okay, so we're going to look at nuclear fission and fusion. Let's start with nuclear fusion. Okay, and both of these can release energy, by the way. Okay, this is when two small nuclei are combined into a larger nuclei. And it's kind of like for fusion of hydrogen happens in the sun. We'll use that as our example here. Okay, let me just see if I can get this. There it is. Okay, get my preview here. Sorry about that. So yeah, about 17 minutes. Okay, so good. Should be able to do fusion and fission. So an example of this, the fusion of hydrogen in the sun. And fuses it into helium. Okay, so what does that look like in a nuclear reaction? Okay, so what we do is what the fusion reaction looks like is it's hydrogen isotope 2 plus another hydrogen. This one has an extra neutron in it. Okay, those things combine together and they produce helium 4 and an extra neutron. So neutrons are being released as well. Plus energy. Okay, and this is fusion. Okay, so we can calculate the energy released if we know the masses of everything using equals mc squared, what the nuclear energy would be as we created there. Okay, so we'll do an example of that in a minute. Let's do also nuclear fission, which I have to bring up here. So let me just pause and bring up my example for that one. Okay, so nuclear fission is this one. Nuclear fusion, or sorry, nuclear fusion is that one. Nuclear fission, you can imagine. Okay, this occurs when a large nucleus splits or is split into two or more smaller nuclei. Okay. Energy is also released. An example of this is the fission of uranium-235. Okay, that's very common. So what the uranium-235 fission equation looks like is something like this. Okay, we take a uranium-235 atom, we whack it with a neutron, okay, and then it splits into two daughter nuclei, this one does, into 140 xenon, which is element number 54, plus, so I had to look this up because I don't memorize this stuff. Neither do you. You just have to be able to identify what's going on. It's 30, what is it, 38. Okay, so that should be 92 on the bottom. And then we also have two neutrons released, plus energy. There is the fission of nuclear uranium-235. So we could do an example calculation using E equals mc squared. How much energy is released by this reaction? What we need to know is the masses of everything here. Okay, we already know what the mass of neutrons are, but if we look up the masses of each nucleotide, okay, so this will be, let's calculate the energy released in this reaction. Okay, and the process is simple. We simply total the reactant masses and the product masses and find the missing mass. Convert the missing mass to energy. So for example, here, if we knew what everything was, so I've looked up, so I paused there for, I looked up all the masses. So we know that U-235 equals 3.9029 times 10 to the negative 25 kilograms. And again, there is another unit known as atomic mass units, but we're going to stick with kilograms. This is 140. Okay, that one is 2.32. Let's see, what is it? 2.3234 times 10 to the 25, negative 25 kilograms. Okay, and then the other daughter album, the strontium, 94. That's 1.5595 times 10 to the negative 25. And we know that a neutron already, we know neutrons from, we've used them before. That's 1.6749 times 10 to the negative 27 kilograms. Okay, so if we know all those masses, what we got to do is we've got to find the reactant mass. Okay, this is balanced. Okay, we've got one neutron here, two neutrons there. Okay, so we're going to add the uranium and the one neutron together. So we're going to do the reactant mass first. Okay, so that would be one uranium. So that would be 3.9029 times 10 to the negative 27 kilograms plus the 1.6749 times 10 to the negative, sorry, this is 5, negative 5, negative 27 kilograms. Okay, when we do that, we should get 3.919649 times 10 to the negative 25 kilograms. Okay, that's the reactant mass. The product mass, okay, so if we do the product mass, we have 2.3234 times 10 to the negative 25 kilograms. Okay, and we got 1.5595 times 10 to the negative 25 kilograms. And we've got two of the neutrons, so two neutrons. So that would be 2 times 1.6749 times 10 to the negative 27 kilograms. And that equals, if we do that one, 3.3498 10 to the negative 27 kilograms. Okay, so then if we combine this one together, we get 3.916398 times 10 to the negative 27 kilograms. So you can see the products have slightly less mass, which means energy has taken its place. Okay, so then what we do is we find the difference in mass. Okay, so what does that look like? Well, this one here is a little bigger. Oops, this is 5, sorry. Got to be careful there. Okay, and if we do the difference in mass, we get 3.251 times 10 to the negative 28 kilograms. Okay, so then after we've got both total masses, reactant and product, and we subtract them, convert this to energy. So convert the mass to energy. Okay, so E equals mc squared, we know that. So in our case, we take our mass, and we multiply by speed of light squared. And what do I get there? When I do that one, I get, looks like 2.926. times 10 to the negative 11 joules. Now you're thinking that, well, that's not much energy, right? But that's per nuclear reactant splitting. So if you think about your chemistry there, and you know that Avogadro's number, 6.02 times 10 to the, what is it now? Times 10 to the ninth, or no, not ninth. Let me look it up here. Okay. So 6.02 times 10 to the 23. So if you assume that you had that many particles in 1 gram of uranium-235, and you went 6.02 times 10 to the 23 times this number, 2.9626 times 10 to the negative 11, you get a number of, oops, sorry, I did it wrong. 6.02 times 10 to the 23 times 2.926 exponent negative 11. You'd get 1.76 times 10, 1.76 times 10 to the 13. So if we divided that by 1,000, because we can make it into kilojoules. Well, even if we did kilowatt hours, you know that there's 3.6 million there's 3.6 million joules in a kilowatt hour. So if I divided this by 3,600,000, we still have 4,900,000 kilowatt hours. 4,900,000 kilowatt hours of energy from 1 gram of uranium. So that's a lot of energy. That's why some nations, and us included, use nuclear power, because it's very prevalent, or you get large numbers of it. Okay, so that's kind of why they use that particular one. So again, we could do, if you go back up to the top here, we could find the energy here as well if we knew the mass of each of these hydrogens. I might put this one on the assignment, maybe, finding the nuclear energy of this, or I might put another fission reaction. Okay, we could find the energy released here as well per fusion. And remember that fusion is forming larger nuclei from smaller ones, and fission is splitting larger nuclei into smaller ones. So that's fission and fusion. Okay, and then of course, if we go back to the beginning, the chain reaction, okay, that's where you have a slow neutron splitting a nuclei and then releasing more neutrons, and then getting an exponential growth, and each of these is releasing more and more energy. And if you have critical mass, this occurs instantaneously or really quickly, and that's when you get the explosion. Okay? All right, so we've kind of covered each of these. I would like to do a fusion example as well, but I think you can try. I'll leave that for next day, as we're into about 35 minutes as well. So next time, we're going to be looking at probably getting into a little bit about nuclear radiation damage and those kinds of things. Okay, we're still in the particle physics area. Okay, so we'll look at that next day.